Alright then, hello everyone. In today's lecture we're going to be going over combinational logic and digital logic. So today we're going to be talking about encoders, decoders, three-state devices, multiplexers, parity circuits, comparators, adders, and arithmetic logic units. As always, if you can always consult Digital Design Principles and Practices, 4th edition, John F. Wakerly, for more information on these topics. So, in digital electronics, circuits are broadly organized into two types, combinational and sequential. Today we're going to be talking about combinational logic circuits, which are digital circuits whose output depends only on the current state of their inputs. They do not have memory elements, meaning their past inputs or outputs do not affect their current output. Think of them as instantaneous function generators. As soon as the inputs change, the outputs change accordingly, after a very small propagation delay. Key characteristics. Outputs are a direct function of current inputs. There are no memory elements, no feedback loops, and can be described by Boolean expressions, truth tables, or logic gates. So the first thing I want to talk about is encoders. Encoders are an encoder is a combinational circuit that converts an active input signal into a coded output, typically a binary or binary coded decimal code. There are two types. Decimal to BCD converts a decimal input at 0 to 9 to a 4-bit BCD output, and a priority encoder. This is a more practical type. If multiple inputs are active simultaneously, it prioritizes the highest number active input and produces its corresponding code. This is crucial to avoid ambiguous outputs. So this is a typical binary encoder. These are the Boolean expressions, and this is the logic diagram for an encoder. So here is an example of a simple binary decimal to binary encoder. Consider an encoder with 4 inputs, I, 0, 1, 2, and 3, and 2 outputs, output 1 and 0, if only one input is active at a time. And here is the truth table. So as you can see, think of the outputs as 0 and 0, 0, 1. So if we can convert that to decimal, we get 1, 2, and 3. And look which inputs are active. When the first input is active, we get output 0. When the second input is active, we get 1. So you can see when this is active, it corresponds to 2. And when if this is active, it corresponds to 3. So pretty simple. Okay, and then a 10-bit then a decimal to binary decoder as well. So this encoder has 10 inputs, D0 to D9, one for each decimal digit, and 4 outputs, B3 to 1 and 0. Representing the 8421 binary coded decimal code. Only one input is assumed to be active at a time. So as you can see, we have the truth table down here. So our outputs. So basically you can see how it corresponds. So 1 is high, 2, 2, 3, 3, where they'll go all the way down to 9. And as you can see, 9 is active. A decoder. A decoder is a combinational circuit that converts a binary code input into a unique output line. For an n-bit input, a decoder can have up to 2 to the n output lines. Only one output line is active for each unique input combination. So a binary decoder converts an n-bit binary input to 2 to the n unique output lines. So as we can see, this is the typical diagram for a decoder. So when it's all 0, the 0th output is low. When 1 is high, the first output is low, and etc. A 3-state or tri-state device. A 3-state device, often a buffer or an inverter, has a third output state in addition to the standard logic high 1 and logic low 0. The high impedance high Z state In the high impedance state, The output effectively disconnects from the circuit, acting like an open circuit. This means it neither drives the line high nor low, and it draws very little current. So this is a standard symbol for either a standard or inverter. So when enable is active, the device behaves like a normal buffer or inverter. So as you can see, here are the truth tables for that as well. A bus driving with tri-state buffers. Imagine a shared data bus in a computer system where multiple components need to send data. If all components try to connect data simultaneously, it would lead to contention and damage. Tri-state buffers solve this. Each component connects to the bus via a tri-state buffer. A bus controller ensures that only one component's tri-state buffer is enabled at any given time. All other components' tri-state buffers are in the high impedance state, effectively disconnecting them from the bus, allowing the enabled component to drive data without interference. So this is kind of the typical application. So if I want to send 3 sets of data, to send them one at a time, I will kind of just use tri-state buffers to disable the data and just send the enabled data along the bus. Multiplexers. A multiplexer or mux is a data selector. It takes multiple data inputs and selects one of them to be passed through a single output line. The selection is controlled by a set of select lines. For n data inputs, a mux requires log base 2 n select lines. So this is to the typical implement logic diagram for a mux over here. Then an example of 4 to 1 mux. So these are select bits, and these are and this is the output. So if it's 0, 0, the 0th input, which is up here, will go out, and if it's 0, 1, the first x input will go out like this. Go on would be equal to f. Parity circuits using XOR gates. A parity is a simple error detection method used in digital communication and storage. A parity bit is an extra bit added to a binary word to make the total number of ones in the word, including the parity bit, either even or odd. In even parity, the parity is set such that the total number of ones is even, and the opposite is true for odd parity. The XOR gate is perfect for parity generation because it outputs a 1 if an odd number of its inputs are 1, and a 0 even if a number of its inputs are 1. For even parity generation, XOR all data bits. The output of the XOR chain is the parity bit. If the data has an even number of ones, the XOR output is 0, making total ones even. Example, parity generation and checking. Let's consider a 4-bit data where D is equal to 1011. Even parity generation, P even, would be one exclusive OR with 0, exclusive OR with 1, exclusive OR with 1, where we get 1. The transmitted data with even parity would be 10111, data plus parity. So if we check the parity of 10114, it's 4, the number of ones is 4, with an E which is an even number, correct. Comparators. A comparator is a combinational circuit that compares two binary numbers and determines their relationship, whether one is greater than, less than, or equal to the other. So here you would have a typical application. So if you wanted to see if A was less than B, then you would use this gate. If you wanted to see if they were equal, you would use an XOR gate. And if you wanted to see if A was greater than B, you would use this configuration. Adders. Adders are fundamental combinational circuits used to perform arithmetic addition of binary numbers. So there are two types. A half adder, it adds two single binary digits, it produces two outputs. A sum, which is A exclusive OR B, and carry out, which is A and B. So a full adder would add three single binary digits, A, B, and a carry in, C in. It produces two outputs, the sum, which is the A exclusive OR B exclusive OR C in, and carry out, which is equal to A and B, or C in and A exclusive OR B, or simplified A and B, or A and C in, or B C in. So this is a truth table for a half adder. This is how it would be implemented, and this is the truth table. A full adder is a little bit more complex. This is how it would be implemented, and this is the truth table that you can see. A ripple carry adder. Multiple full adders can be cascaded to add multi-bit numbers. For example, to add two 4-bit numbers, A3, A2, A1, A0, and B3, B2, B1, B0, you would use 4 full adders. The carry out Cout 0 from the least significant full adder becomes the carry in for the next full adder, and so on. This is simple to implement, but it can be slow for large numbers, due to the ripple effect of the carry propagating through each stage. An arithmetic logic unit. An ALU is a core component of a CPU that performs arithmetic and logical operations on binary data. It's a complex combinational circuit that usually includes arithmetic operations, logical operations, and shift operations. An ALU takes 2 input operands and a set of function selection lines that determine which operation the ALU will perform. It also has status outputs like carry, 0, negative, overflow flags. A simplified ALU structure and operation example. Consider a simple 4-bit ALU that can perform add, subtract, and OR operations. It would have 2 4-bit data inputs, 2 function select lines, and a 4-bit output with status flags. And the internal structure might involve an adder-subtractor circuit, an AND gate array or OR gate array, and a 4-to-1 multiplexer for each output bit. So, as you can see, this is the truth table for such an operation. So if S1 and S0 are 0, 0, the multiplexer would select the output from the AND gate array to be the ALU's final output. If S1, S0 is equal to 1, 0, the output from the adder would be selected. Alright, thank you very much. In the next tutorial, we'll be going over sequential logic.